We're going to look now at just simply adding fractions with the same denominator. And we can always use money as an example. It's always a nice thing to look at when you're talking about this. We know a dime is a tenth of a dollar. And so if I want to add 2 dimes together, that's 10 cents plus 10 cents equals 20 cents. What must I do? Let me write this as a fraction in terms of a dollar. 1/10 of a dollar plus another tenth of a dollar, amazingly enough, is 2/10 of a dollar. You see, if you have the same denominator, you can just add the numerators because you're adding the individual slices, the individual pieces. Let's look at a few other examples of slicing up a pie. Suppose we have 6 slices and we want to add 2 different sets of pieces of something made up of 6 slices. So I have 2/6 plus 3/6. How many do they make up? Well, I could count the number of slices in the answer there, or I can write it as a fraction. 2/6, 2 of 6 things plus 3 of 6 things will give me, if I just use my fingers to count, 5 of 6 things. Here's another example. Suppose now I have 5 whole pieces in whatever I've cut up. And I have pieces of this now. I have 3 of the 5 plus 1 of the 5. And as we can count here, because the pieces are pretty big and we can count them, that's 4 of 5. We write it mathematically as 3/5 plus 1/5 is equal to 4/5. And we see that 3 plus 1 is equal to 4. Let's see if we can generalize this into a rule. We can do it this way. Suppose I have D pieces. Whatever D is, it could be 2, it could be 10,000. And I have A of D pieces and I'm adding B of D pieces. What do? I add A plus B and put that in the numerator of the fraction, put the sum of those things in the numerator of the fraction, and leave the denominator the same. I would write it this way. I add the numerators and I keep the denominator. Let's look at another case that uses this that might be more interesting. And again, just to review with you before we go on, if I have 3 of 10 and 4 of 10, I put the 3 plus the 4 in the numerator in the top of the fraction, keep the denominator the same. Keeping that in mind, let's look at this one and see what we do with it. I have here a total of 5 pieces. And I want to add 4 of those 5 to another 4 of those 5 pieces. What's going to happen here? When I finally do this, I find I have 8 pieces. 4 plus 4 is 8, but if I have 5 total, what that means is that I'm going to have more than a whole thing. And when I start to count pieces, 5 of those pieces make up the whole thing, then I have 3 more left over. Let's see how we would express that mathematically. 4/5 plus 4/5 is 8/5. But you see, that's an improper fraction. What I need to do is then change that to a mixed number, and 5/5 is 1. That leaves 3 from the 8. So my final answer there is 1 3/5. Let's do another one of those just to see how it goes. I have 7 pieces total, and I'm going to take 3/7 and 5/7 and add those together to see what we get. I find I can take the 3 and the 5/7, make one whole pie, and then have one more left over. Let's express that mathematically. 3/7 plus 5/7 gives me 8/7, an improper fraction. I need to change that to a mixed number, and when I do, I get 1 and 1/7. Let's switch gears a little bit from adding to subtracting fractions with the same denominator. Again, let's suppose I have 7 pieces total, and I have 3 pieces of those 7, and I want to take one away. I want to eat one of those, or give one to a friend, or whatever. If I take one of those away, I find that I have 2 left. 3/7 minus 1/7 is equal to 2/7. Let's look at a problem based on this. Jack's gas gauge reads 7/8 of a tank at the beginning of the day. At 5 p.m., the gauge reads 1/8. How much of a tank full of gas has he used that day? And if he gets 240 miles on a full tank, how far has he driven? Let's take this piece by piece. First, we'll look at what's given. We have 7/8 of a tank to start, 1/8 of a tank to end, and then how much of a tank full will he use is one of the questions asked. We're also given that there's 240 miles on a full tank, and then we'd like to know, based on how much of a tank has been used, how far has he driven? We're given 7/8 full, 1/8 full, 240, and we're asked a couple of questions. Let's suppose that's the tank of gas, and it's 7/8 full in the morning and 1/8 full at night. We want to know, again, how much has been used. We're asked for a difference. Whenever you're asked for a difference in a problem, that means that you're going to do some kind of subtraction. We take 7/8, subtract 1/8, we see that's 6/8, and I notice right away that there's a common factor of 2 between the numerator and denominator. I can reduce this to 3/4 of a tank. Then what I want to do is see, all right, if I've used 3/4 of a tank and I get 240 miles on a full tank, how much have I driven? 3/4 of, remember, of you usually indicate with multiplication. 3/4 of 240 is, we've seen how to do this in class 7, multiply numerators, multiply denominators. I get 7/24, which of course is an improper fraction. When I reduce this, I get 180 over 1. 3/4 of a tank would mean that I've driven 180 miles. Then I can check this. I can ask, is 180 3/4 of 240? 180 over 240, and I can reduce this to lowest terms, is in fact 3/4. This tells me that there's a very, very good chance I've done this problem correctly. Again, just to review here, if I'm subtracting fractions, you see I have d things, a minus b of them. I subtract the numerators, and I keep the denominator. And this would be an example. If I have 3/7 minus 1/7, I'm left with 2/7. 3 minus 1 is equal to 2. Switching gears very slightly, let's look at dealing with sign numbers, numbers on the number line, where we now have fractional values. And we keep the same denominator, but we generalize our rules a little bit more to look at adding negative numbers the same way we did quite a few units ago. I want you to remember something that's pretty important when you're dealing with fractions. If you have minus a over b, you can write that in 3 different ways and use it based on how valuable the information is to you in terms of the problem. Minus a over b is exactly equivalent to minus a over b, or a over minus b. Those are 3 identical numbers, if you want to call it that, and you use them as you need them. Knowing that, let's take a look at writing this as a signed number. We have 3/8 minus 5/8. Right away you know that if you're going to take 5 from 3, you're going to wind up with something negative. Let's write this in much the same way as we did when we were looking at integers in terms of signed numbers. I can write this as plus 3/8 plus a minus 5/8. Then I can add those two just as I added signed integers, thinking about the number line. In other words, I walk 3 blocks or steps or feet or whatever to the right. Then I look at that and it looks to me like I add or walk 5 to the left going in the negative direction, and I'm left with minus 2/8. Remember now when I showed you that flash from the past, that's exactly equivalent to minus 2/8. But I'm not quite done yet because I know that 2 and 8 share a factor of 2. To reduce that to lowest terms, I need to do that. Divide the numerator and denominator by a 2. In other words, what we want to say here is that all of the operations that you normally do with integer math work when you're dealing with fractions as well. Here's another example. Minus 3/16 minus 5/16. I can rewrite this way. It's minus 3/16 plus a minus 5/16. When I work that out, minus 3 plus minus 5, 2 trips to the left, gives me minus 8 over 16, which I can rewrite as minus 8/16. Again, our flash from the past. And I look at this again and I see that there is a common factor of 8 between the numerator and denominator, which I can divide out, leaving me with minus 1/2 as my result, reduced to lowest terms. Let's try yet another one. We have to be a little bit careful here because we have now a minus 5/19 minus 7/19. We'll do the same thing. First we can rewrite this as a signed number in the numerator. Then we see we have a minus 7. That gives me minus 5/19 plus 7/19. Minus 5 plus 7 gives me a final result of 2/19. And I look at that and there are no factors in common between 2 and 19. That fraction is reduced to its lowest terms and I'm finished. Here's another one. 2 mixed numbers, 5 1/3 plus 2 1/3. There are a couple of ways of going about this, remembering that 5 1/3 is 5 plus 1/3 and 2 is 2 plus 1/3. If the problem is simple like this, you can add the integers. 5 and 2 is 7. Then you can add the fractions. 1/3, 1/3 is 2/3. So we know that the answer is going to be 7 2/3. But in general, it's easier to do a problem like this by changing those mixed numbers to improper fractions. Let's actually do the problem that way. I change 5 1/3 to 16/3. I change 2 1/3 to 7/3. I add those two. 16 plus 7 is 23, and I wind up with 23/3, also an improper fraction. Now I have to translate those back, and I get 7 2/3. We've seen how to do a lot of operations now with numbers. Let's go now from numbers to quantities containing numerals and unknowns, numerals and variables. First, let's review a little bit. A rational number. It's rational because it can be expressed as a ratio of integers. And we also remember that we have like terms if we're dealing with numbers and variables multiplied together. So for example here, we have 5 times the quantity x squared plus 2x squared is 7x squared. Notice here we have only an x squared in both of those terms, so we can add them together. But if we had 5x cubed and 2x squared, I have a cubed in one term and a square in another term. Those are not like terms. Let's look at a fairly straightforward example to start with. Using the same rule, a over d plus b over d is the sum over d. Now you see we're not dealing with just numbers anymore. We're dealing with algebraic quantities. But I proceed exactly the same way. I see I have the same denominator in both cases, so I can add these rather directly. Put them both in the numerator, x plus 3x. Those are like terms because they both have x only to the first power. 3 plus 1 is 4x over 5 is the result of that calculation. Let's try one that's a little more interesting. I have n plus 1 over 12 plus the quantity 2n minus 2 over 12. We'll proceed exactly as we did before. Put the two quantities added together in the numerator over the same denominator. Now I need to work this out. N plus 2n is 3n, plus 1 minus 2 is minus 1, and my final result is 3n minus 1 over 12. Here's one that might be a little bit more interesting yet. It's 2x squared minus x plus 5 fourths minus x minus 2 fourths. We put them both in the numerator over 4. Then I simplify. And remember that when you have minus something in a bracket, to remove the bracket, you change the sign of both of the terms. When I do that in the third line, I see I have a minus 2x and a minus x. Those are like terms. When I'm finished, I get 2x squared minus 3x plus 7, all over 4. Here's another example that's a little bit different because it has a variable in the denominator as well as in the numerator. But if we see that we have 2x in both of those denominators, we have fractions that we can add together because those are like terms. It's the same denominator. Let's go through the same procedure. We put both of the numerators together. Then in order to, again, to perform this operation, which is a subtraction, we know we have to change all of the terms in those brackets, in the parentheses, to the opposite sign. 6x squared becomes minus 6x squared. Minus 3x, minus times minus is plus, becomes plus 3x, minus a plus gives us a minus 3. Now we can collect like terms, and when I do that, I see that I have a 3x and a 3x, which gives me a 6x, plus 7 minus 3 is 4 over 2x. I might think I'm done here until I notice something. It looks to me like there's a factor of 2 in every one of the terms in the numerator, in the top. I have a 2x squared plus 6, which is 3 times 2, plus 4, which is 2 times 2, and I have a 2 in the bottom, 2 times x. Suppose I pulled the 2 out, factored the 2 out. Now I see clearly I have a 2 over 2. 2 over 2 is 1. I can say that the 2's cancel. The best final result, reduced to lowest terms, is this. It's x squared plus 3x plus 2 over x. I've gotten rid of any terms in the numerator and denominator that are the same. But notice again what I did in the top. In order for me to factor out a 2, every one of the terms in that polynomial in the numerator must contain a factor of 2 for me to do it. If one of them didn't, I would be stuck. I couldn't go any further than that. Let's get into the heart of why we split adding and subtracting fractions out from multiplying and dividing fractions. And this comes when we need to deal with fractions with different denominators. In order to introduce this topic, I'd like to show you a little video that we made here. Hi, I'm doing good. Let's see. I'd like to order a pizza. I'd like a medium with green pepper and mushrooms, please, and a pitcher of cola.
And how many comes for that pitcher?
4 of 4, please. Okay, thanks a lot. Wow, that looks really great.
Hey, not fair. This pizza is cut up into 6 pieces, and we're only 4 of us. That means that 2 of us won't get our share.
No problem. What we can do is this. We can cut each one of these original slices up into 4 so that each of us can get 1 piece from each original slice. Then we'd all get the same amount.
Okay.
Well, wait a minute. If you do that, you're going to cut this pizza into 24 teeny tiny little pieces, and you're really going to mess it up. How about this? Let's cut each piece into 2, and then there'll be 12 pieces, and there's 4 of us, and 4 divides into 12, and we'll each get 3 pieces.
Okay, that makes sense. I'll do that. Okay, that should about do it.
All right.
Wait a minute, you guys did too much work here. We could have just taken 4 big slices for each of us and cut the other 2 in half.
So the point of that video was that if you have different numbers of pieces when you're trying to fit it, what you need to do is find some sort of a common division between the 2 different states. Let's see more about how that would work to get the idea, and you'll see what I was getting at in that video. Suppose I want to add $0.25 to half a dollar. That says I need to add 1/4 to a half, but notice that the 2 denominators are different. I'm talking about different size slices. The point here is, what can I do to the half dollar or the $0.25 or both of them so that I have the same number of slices? What I can do is split that half dollar in half, make that 2 quarters. Now I've done something so that I have exactly the same denominator by changing one or both of them to a common denominator, 4 in this case. Now I can add them. 1/4 plus 2/4 is 3/4. What you want to do is upscale the fractions, one or both of them, without changing their value, 1/2 and 2/4, exactly the same value, but now I have a common denominator, 4, and then you just do the math. Let's take a look at some pies that I brought along just to emphasize this point. Here are 2 pies. This one was cut into 4 pieces, and there's 3 of 4. This one was cut into 6 pieces, and there's 4 of 6. I didn't want to waste your time having you watch me cut these pies up, but what I've done is I've divided the 2 pies into equal pieces by, first of all, knowing that if I have quarters, I can divide each of the quarters into 3 to get 4 times 3 is 12 whole pieces. And here, since I had 6, if I divided each of the pieces in half, I would also have a whole pie of 12 pieces. Now I can, since both of these pieces were divided into 12s, notice that they're pretty much the same size. Now I could add the 2, 4, 6, 8 twelfths I have with this pi, and the 1, 2, 3, 4, 5, 6, 7, 8, 9 twelfths I have with this pi to get 17 twelfths, or 1 and 5 twelfths of a pi. And so what I've done is I've found a common denominator and was able to cut things into the same size. That's what you're doing when you look for a common denominator in fractions. And since I have these pies cut up, I think I'm going to have a piece on the way back to the desk. Delicious. Well, I'll have the rest of that later. Let's continue. Here, in fact, is a problem about pies. At the end of the day, Chuck's Diner has 2 slices of apple pie that was originally cut into 6 slices, and 1 piece that was originally cut into 4 slices. How much pie remains? I can still taste the pie. Here's what we're given. We want to know how much pie remains. So what I need to do is find the same size, 2 pieces of 6, 1 piece of 4. 2 6 plus 1/4. I need to represent those as the same. What about 12 pieces? As I did before, I have a quarter and a sixth. 2 6 plus 1/4 is going to give me 4 twelfths plus 3 twelfths by multiplying numerator and denominator of one by 2, the other by 3. Now I can do it, and I have 7 twelfths of a pie left at the end.